Hello everyone, I'm Aastha Sharma.
I'm Moulik Srivastava.
I'm Pranjal D.
We all are pre-final year students at Jaypee Institute of Information Technology, Noida. We are also digital design trainees at PinE Training Academy. We joined PinE in our second year, and now in our third year, we are working on an internship project assigned by August Technology Private Limited. This project is made using Verilog. In this project, we are implementing a 4-bit ALU on SSD, LCD, and VGA using the UART protocol. Now we are ready for a demo. So, as I discussed, the project is implementation of a 4-bit 31 operation ALU on the different display device. ALU. ALU is arithmetic and logical unit. Our ALU is designed to perform 31 different operations, which include a lot of arithmetic, logical, and shift operations. Now, our ALU has two inputs, A and B. Both are 4-bit files, and their values can range from 0 to 50. We also have a 5-bit select line that allows us to select from the 31 different operations. We can use the select line to give the proper operation that we want to perform. Then we have control systems. There is a 2-bit control line that is used to select the sign of our operands A and B. That can be positive sign. Now, I would like to invite Moulik to take you forward in this presentation.
Okay. Thank you, Asta, for the great introduction. Now we'll move forward. Now, once the ALU is implemented over the FPGA, once the processing has been done, the second most important part of any machinery is how interfacing is done, how we interact with the humans. So now we'll come to the displays. The first displays are 7-segment display. Now the 7-segment display attached with the FPGA board, which is Basys 3 in our project, is common cathode 7-segment display, where there are 4 SSDs attached to each other. After that, we will do the segment configuration and then the common cathode part. As we can see, there are anodes and the cathodes. The anodes, basically, they control which SSD would be switched on or switched off at a particular moment, and the cathodes would be responsible which digit would be displayed. Now, at a particular time, only one of the SSDs would be switched on, and then we would do the switching between the different SSDs so that we can display all the result at the same time. Now, the switching is done at such a speed so that the human eye can see that all the digits are displayed at the same time. Now, after the SSD, the second display is PMOD CLP LCD. Now, PMOD CLP is made by Digilent, and we have used this for Basys 3 because it is the most compatible part. Now, in PMOD CLP, there is an interface, then there is the pin usage, and there are the timing requirements. In the For the pin usage, there are 8 data pins and 4 pins which control the voltage requirements, which are ground and VCC.
VGA. VGA stands for Video Graphics Array. It is a display standard that is commonly used in televisions and monitors. This is a VGA port. I'm sure you must have seen this somewhere. Now, what is exactly a VGA? As I discussed, VGA is a display standard. It basically uses 3 different colors to perform its display. The 3 colors are red, green, and blue. Each color gets 4 bits that makes a total of 12 bits. These 12 bits are used to assign the color of a particular pixel. Now, VGA also have sync pulses, which are used for their timing. Now, if I talk about the VGA display, VGA is basically a grid of pixels. There is a cathode ray tube inside the VGA display, which lights up the pixels one by one from the top left corner to the bottom right corner. And according to the assigned values, all the pixels get their assigned colors. Now, this type of scanning is called raster scanning, in which we scan each pixel one by one in a row. VGA uses 2 sync signals that are H-sync and V-sync. H-sync stands for horizontal syncs, that is used to mark the end of a row and tells the VGA controller to move to the next row. Similarly, V-sync is used for marking the end of a frame and tells the controller to start a new frame, that is to go back to the top left corner pixel. Then this is the VGA display diagram. This surface over here is the display surface, and it has the resolution of 640 into 480. That is, we have 640 columns and 480 rows in our VGA display. Now there are two time frames or time phases, I can say, front porch and back porch. These are the times where no data is actually implemented or actually displayed on the VGA. This is the time when the VGA controller takes rest. We can say that it prepares itself to retrace again. And during this time, the coil of the cathode ray tube decrease its currents. That is, the cathode ray tube basically stops working, or the current in the coil decreases, so that no information is displayed. And during the display part, that is the forward beam, the current in the cathode ray tube rises. Then the working of code. We are using the Basys 3 FPGA board for the implementation of our project. Basys 3 runs on a frequency of 100 megahertz, but the VGA controller works at 25 megahertz. So we implemented the clock division to get the required frequency. Then the second part was signal generation. We generated a lot of counters to keep the track of the different pixels during the VGA display. The third and the most crucial part is handling dynamic data. As I discussed earlier, the output of our ALU is a 13-bit number. So the input to our VGA is a 13-bit number. The MSB is used to extract the sign of the output, and the remaining 12 bits are used for the final answer. Now, if the answer is negative, we do the 2's complement of the 12-bit number. The next step is to convert into the ASCII value. Basically, the 12-bit part is converted into its decimal equivalent, and then from that decimal number, we extract each of the digit one by one and convert them into their ASCII values. The last part is using a character module. We have created a separate character module in which we have all the representation of characters which we can use here. And by the ASCII value which we got from the last step, we can get the character representation of that particular value or character, and we use these representations to display our output.
Now, starting with the last part of project is UART protocol. Now, if we talk about UART, UART stands for Universal Asynchronous Receiver Transmitter. When we come to asynchronous, this is the most important part of UART. Why? It is a gift because when we have asynchronous, we don't need a common clock, because making a common clock for two devices is a very tough thing. And it is also a boon at this boon and curse at the same time. Why? Because if we have to give the same, because we have to generate many counters so that we keep record of the bits in which order they are sent and in which order they will be received. After that, we have the receiver and transmitter part, which will be attached separately. Now, coming to the Basys 3 board, we have JTAG 17, where the pins A18 and the pins B18 are separately responsible for transmitter and receiver of the UART. After that, we use the FPDI FT223HQ USB, which is actually a converter from serial to USB port, which works on the system or the laptop or the PC to which we'll be attaching our Basys 3 board. Now, baud rate and FPGA. The most important part of UART is baud rate. Why? Because baud rate is responsible for the asynchronous connection of the two transmitter and the receiver. We need to give the same baud rate. We need to run the same counters so that our transmitter side and the receiver side know at which time and at which bit has to be received. After now we'll come to the baud rate calculation. For our project, we have used 9600 baud rate, which is one of the standard baud rates used in most of the projects. The other baud rates are 11, 1000, 115200 and 19400. Now, why baud rate calculation is very important? Because our Basys 3 board works on 100 megahertz of clock, which means it can send 100 megahertz bits, 100 like 10 to the power 8 bits in 1 second. But we need 9600 bits, so we need to slow down our Basys 3 board. For that, we need to run counters between each set of bits. Now, after that, this is the transmitter state machine, which is first of all, our transmitter would be in an idle state where no bit is transferred, the machine is at rest. Then we'll send the start bit. After that, we'll send the data bits and then the stop bit to signal to for the receiver side to stop the receiving. Now, after the transmitter side, we have the receiver flowchart. Again, we will first receive the start bit from the transmitter, which will indicate that the receiving has to be start. Then we'll start receiving the data bits, and after that, we'll start get the stop bit, which shows that yes, all the bits we have received are correct. Otherwise, there could be a mistake in the bits. Now, after that, there's UART and ALU integration. Now, a very important question comes. We made ALU, we did interfaces. Why we need UART for this project? UART basically allows us to give inputs and outputs from different devices. If we want to put input from a keyboard or from a separate device apart from our FPGA board, we need UART connection or any other serial communication protocol for that. For this project, we choose UART. Now, for ALU integration, we had to give multiple inputs, and UART actually gives one data bit at a time. So, for multiple inputs, we attach data frames for the UART. Like, for example, if one data frame has been sent to the whole UART communication protocol, then the data frames shift to the next, and after that to the next, till the last frame has been sent. From after that, we receive at the FPGA board. Then the ALU processing has been done, and after that, we connect to the VGA, LCD, and SSG part, where all the outputs have been are displayed as Aastha presented in the chart. Now, a complete demo of this part would be presented by our partner, Pranjal.
Thank you, Moulik and Aastha, for the overview of this project. I, Pranjal D, will be giving the demo of the project. So here is the code for the top module of our project, where we have connected our submodules of ALU, LCD, UART, SSG, and VGA. And here is the code for ALU. As Aastha gave us an overview, we are performing our 31 operations in the ALU part, the LCD part for the output of this project. Here is the code for the LCD, and UART code for the keyboard interfacing, as explained by Moulik, and SSG again for the output, and VGA for the output. So now I will be showing the simulation window of this project, where we have simulated it virtually. So now I'll be showing the synthesized design generated by our software. Here is the design. We'll go to this open synthesized design, then schematic. So this is a netlist generated by the code, netlist of the code generated by our tool. Okay, so now we have already generated a bit file which we have implemented on our Basys 3 FPGA board, and the output can be seen on the LCD, SSG, and the monitor screen via VGA. To give the inputs, we'll be using Teraterm, and now I'll be opening. Here is the Teraterm and the ALU code. From here, we'll be selecting our COM port, which is connected to this board. After doing that, we can give our input from the keyboard. So for the first operation, like I'm performing an addition operation, I'll be giving maximum input can be given as 15 in either of the inputs. So initially, I'm giving 15, and addition operation. Your addition operation select line is 0, 1. So 0, 1. Sign initially, I'm giving positive for both of them. 0. So as we can see, our output is coming out to be 30. That is 15 plus 15, 30 for the addition operation. Similarly, we can give inputs for other operations like 15 into 15, we can do multiplication, 15 into 15. Then select line for multiply 0, 3, and sign will be 0. So we can see the multiplication of 15 into 15 is coming out to be 225 when both the numbers are positive. If we want negative, then we can also do that. Again, we'll give 15, 15, 0, 3 for the selection of the operation, and then 1 for selecting whether the number is positive or negative. So now we can see that is 15 minus 15, that is minus 225, can be seen on the VGA, can be seen on a monitor screen via VGA and SSG and LCD also. Here the SSG and the LCD. For SSG, the 225 number is showing on the SSG, and the negative sign will be shown on this LED, because all the 4 SSGs are using the displaying for decimal numbers. And the LCD output will be shown.